Okay, welcome back to the series of lectures on transform calculus, and in the last lecture we have seen how to apply this idea of Laplace transform to solve different kind of initial value problems, boundary value problems, integral equations. So, we mainly discussed in the last lecture solution of ordinary differential equations, where we had only one independent variables. So, today we will extend this idea of solving differential equations using Laplace transform to partial differential equations. In general, partial differential equations are difficult to solve, but using the Laplace transform some of the partial differential equations can easily be solved. So, today we will continue with this discussion on application of Laplace transform to partial differential equations. So, before we go for solving partial differential equations, I will briefly introduce the partial differential equations. So, the general second order linear partial differential equation, PDE, linear partial differential equation, can be written as a del 2u over del x square plus b del 2u over del x del y plus c del 2u over del y square plus d del u over del x plus e del u over del y plus f u plus g is equal to 0. So, here a, b, c, d, e, f and this g are functions of x and y, or they are constant, or they are simply constants. So, we call this, there is a classification for this partial differential equations, and we call this PDE 1 elliptic if this p square minus 4 ac is negative, and we call the PDE hyperbolic if b square minus 4 ac is greater than 0, and parabolic if b square minus 4 ac is equal to 0. So, the standard examples for this, the one is the heat equation. The heat equation, and this equation models the phenomena of conduction of heat in a solid. So, this equation is del u over del T and some constant, which is the material constant, del 2u over del x square. And if you see here that a is alpha, and we have b 0 and c 0. So, b square minus 4 a c will be so b square minus 4 a c, it is a 0. So, this equation is parabolic, So, this was the example of parabolic equation. We have also the wave equation, and in this case the equation is del 2u over del t square is equal to alpha square del 2u over del x square, and in this case this a is alpha square, b is 0, and then c is minus 1. So, b square minus 4 a c, it is a positive. So, we have this hyperbolic equation. This is also called this hyperbolic equation. Number 3, third example, we have the Laplace equation, and also a different variation of as the Poisson equation, and these equations are del 2u over del x square plus del 2u over del y square is 0, then this is called the Laplace equation, and if this is a function of x y, then this is called Poisson equation. And in this case we have the A is equal to c, and this is 1 and b is 0. So, the equation is elliptic equation because b square minus 4 ac is negative. So, this equation is elliptic equation. Okay, so in we have this according to different classification, we have different equations, and in order to obtain a unique solution of the partial differential equation, we have to supply some initial and boundary conditions together with these partial differential equations. So, that part we will consider while discussing the examples. So, now we come to the working steps, and the working steps in these cases also the same what we have seen while solving ordinary differential equation. So, we will apply the Laplace transform to both the side of the equation, and then we will get a rather simpler ordinary differential equation that can be solved. And again we take the inverse Laplace transform to get the solution of the given partial differential equation. So, the working steps. So, if one of the independent variables in partial differential equation ranges from 0 to infinity, then Laplace transform may be used to solve partial differential equations. So, we mainly solve the heat and the so for example, in the heat equation we have this t variable which ranges from 0 to infinity, and also in the case of this wave equation, and this wave equation models the phenomena of the waves, sea waves or waves in a string. So, in this case also t starts from 0 and we can go up to infinity. So, here also we can apply the Laplace transform. So, we mainly apply these to wave equation and the heat equation. So, the steps are again the same. So, we take the Laplace transform with respect to the variable that ranges from 0 to infinity, and this will convert PDE into an ordinary differential equation. And the second step, the transformed ODE must be solved considering the given conditions. And the last step, we take the inverse transform, and that results the required solution. The required solution. So, before we move to demonstrate the application of Laplace transform to a variety of partial differential equation, we need to address some some points. So, these points are basically, so we denoting the Laplace transform of the unknown variable u x t. So, we have two independent variables x and t. So, we denote this Laplace transform and with respect to t by u x untouched and this with respect to t. So, here this transformed variable s will come, and we have by the definition that this u x s is the Laplace transform of this u x t, and this is 0 to infinity e minus s t and u x t dt. Using this definition, we have the following results that will be useful while solving partial differential equations. So, we have the Laplace of del u over del x 0 to infinity e minus s t and del u over del x dt, and we assume that this differentiation under the integral sign is valid here. So, we have d over this is equal to d over dx 0 to infinity e minus s t and u x t dt. So, this is nothing else but d over dx and u of x s. This is the Laplace transform of u x t as per our definition. So, what we see here, the Laplace transform of the derivative is the derivative of the Laplace transform. We have the next result that the Laplace transform of del u over del t, and in this case we have here time variable and this t variable, and we are taking the Laplace transform with respect to this t variable. So, we have then 0 to infinity e power minus s t and del u over del t dt. Thus, by parts we can integrate. So, e minus s t u are the limits, and then we have minus 0 to infinity u and minus s e minus s t and then dt. So, if we assume that u is of exponential order, then this will go to 0 as this t approaches to infinity, and then we have minus and this as t goes to 0. So, you have u x 0 with minus sign and then minus minus plus s 0 to infinity, and we have here u e minus s t and dt, and this is the Laplace transform of u. So, we have the result that the Laplace transform of del u over del t is simply s, and this Laplace transform of u x t we denote by u x s and minus u x 0. So, it is again the derivative theorem what we have in case of this one variable. Now, we do need again this for the second derivative. So, we have the Laplace transform of del 2 u over del x square, and here we do not have to prove because we did already for the single variable. So, the Laplace of this double derivative will be the double derivative and the Laplace of u. So, that is u x s. The next we have the Laplace del 2 u over del t square, and now here we have t. So, we need to go for the derivative theorem, and similar to one dimensional case or ordinary differential equations case, we have here x s minus s and u x 0, and we have the derivative of u with respect to t and at x 0. So, this is for the second derivative, and the Laplace for this del 2 u over del x del t for the mixed derivative. So, for the x we will not touch. So, we will keep this as it is d over dx, and then the Laplace transform of del u over del t, and that is as per the definition we have u x s and minus u x 0. So, this is s is constant with respect to this x. So, d over dx and u x s minus d over dx u x 0. So, this is for the mixed derivative. So, in addition to that assumption, what we have in this case, that the derivative we can take out of the integral. We need one more assumption. So, that assumption is that if the limit x tending to x 0 and the Laplace transform of this u x t dt. So, the assumption is that the limit we can take inside the integral, that means the limit x to x 0 u x t and dt. That means the limit of x tending to x 0 of the Laplace transform of u x t will be equal to the Laplace transform of the limit. So, limit x tending to x 0 u x t. So, with this information we can now continue for solving different differential equations, and we take a very simple example first. So, here solve del u over del x del u over del t, and we have u x 0 x and u 0 t is t. So, this is the initial condition at t is equal to 0, and this is the boundary condition. So, at x is equal to 0 the value of u is given. So, we take the Laplace transform, taking Laplace transform both the side, what we get here d over dx, and the Laplace transform of u we can denote it by u x s, and we have here the derivative theorem s u x s minus u x and 0. So, this u x 0 is given x. So, we have the d over dx of u x s minus s u x s and is equal to minus x. Yeah, one more point here one should mention that in this case we have both the variables here from 0 to infinity. So, t starts from 0 and we do not have the upper bound for t, as well as for x it starts from 0, we do not have the upper bound. So, we can take the basically Laplace transform with respect to x as well. So, this is minus x, and then we can solve this linear differential equation, and the integrating factor is e power minus this s and dx. So, it is e power minus x, and therefore, the solution would be u x s and e minus s x. Then the right hand side here we have x, the integrating factor, and then constant. So, this we can take we can again apply the integration by parts technique. So, we have minus here x and this e power minus s x over minus s and minus. So, the differentiation of this x is 1 and e power minus s x over s. So, here we have then the plus. So, we can anyway one minus was here. So, we get the minus and that minus will be plus. So, we have minus here and then s, and we have dx and a constant. So, what we have x e minus s x over s, and once again we differentiate this. So, e power minus s over minus s. So, we will get plus 1 over s square e minus s x and plus c. So, this is our u x s e minus s x. Now, we get the u x s u xs will be x over s plus 1 over s square and plus c e s x. The boundary conditions we have to use now. So, v 0 u at x is equal to 0, t was t, and if we take the Laplace transform both the sides, so what we get u 0 s, that is the Laplace transform of this u 0 t, and this is t. So, we have 1 over s square. So, if we go back to this equation, put x is equal to 0. So, we have 1 over s, x is equal to 0, we have again 1 over s square, sorry, and then we have here 1 over s square and plus c e s x. So, what we see from here that c must be 0. So, we get this constant c should be 0, and then our solution is u x s is x over s plus 1 over s square. And now, we take the inverse Laplace transform to get the solution. So, you have e u x t, and this x, the Laplace inverse of 1 over s, that is 1, and Laplace inverse of 1 over s square, that is t. So, our solution is x plus t. Okay, so we go for the another case now, and now we take a bit complicated partial differential equation. So, in this example we have del u over del t plus x del u over del x is equal to x for x positive and also t positive, and with the initial and boundary conditions. So, we have these conditions: x 0 is 0 for x positive and u at 0 t is 0 for t positive. Now, the similar steps. So, we take the Laplace transform, and we have in this case here s u x s minus u x 0 and plus this x d over dx, and the Laplace of this u will be u x s, and the right hand side the x Laplace transform of 1, that is 1 over s. So, for s positive, and this will lead to the differential equation d over dx of u x s, and then we have here plus s over this x and u x s. U x 0 is 0. So, this will disappear, and then we have is equal to, we are dividing by x. So, here we have just 1 over s. So, this is again a linear differential equation, and in this case the integrating factor to solve this would be e s over x dx. So, this is e, and we have s ln x. So, this will be just x per s, and the solution then u x s would be the integral of this x over s and x power s dx plus c. This is x power s plus 1, which after integration will give x s plus. So, we have here sorry. So, here we have the u x s multiplied by this integrating factor. The right hand side we have only 1 over s. So, 1 over s x s dx plus c. So, in this case 1 over s, and the integral would be x s plus 1 over s plus 1 and then the constant. So, what we have then here x power s plus 1 over s and s plus 1 and a constant. So, this is here u x s and x power s. Now uxs, or now let us consider this equation itself and get this constant c. So, our boundary condition was, or the second condition was, that u 0 t is 0, and this will give us that u 0 s is 0. So, now we use this condition here. So, this is 0 and x is 0, this is 0, and this will implies that our c is 0. So, our u xs is x power s plus 1 over s and s plus 1, or we have u xs is x over s and s plus 1, and then we do partial fractions. So, we have 1 over s and minus 1 over s plus 1. Now, taking the inverse Laplace transform, we get u x t as x and the Laplace inverse of 1 over s, that is 1, minus the Laplace inverse of 1 over s plus 1, we have e power minus t. So, this is the solution. So, we consider one more example of a similar kind of first order partial differential equations, and then we will move to the second order differential equations. So, here we solve the x del y over del x plus del y over del t plus a y and b x square, x positive and we have t positive, and with the given initial conditions that y 0 t is 0 and we have y x and 0 is 0. Take the Laplace transform. So, we have x and d over dx, Laplace transform of y, we take y x s and minus y. Okay, this is for this, then del y over del t. So, we have plus and then s y x s minus y x 0 or 0 plus, because here the initial condition is given at 0 plus. So, we have in this derivative theorem 0 plus, and then plus a y x s. The right hand side we have b x squared as a constant we treat, and the Laplace of 1 would be 1 over s. So, we can simplify now. So, this term will vanish because this is given as 0. So, we have simply x dy over dx plus s plus a and y x s, and the right hand side b x square over s, or we have dy over dx plus s plus a over x y x s, and then b x square over s positive. So, we do not have a problem in the division. In any case, if some other stuff appear here, for example, s minus 2. So, we can take this s sufficiently large. So, there is no point of having any problem while dividing this by s or any other term which contains s. So, we have the integrating factor in this case again, that e power s plus a over x and dx. So, this will be e s plus a and ln x. So, this will give x s plus a, and then the solution y x s plus a integral, the right hand side we have b x. So, we have divide by x. So, we have here b x over s. So, we have b x over s and x s plus a, and we have dx and we have a constant. So, here we have x power s plus a plus 1. So, we integrate this. So, we get y x s plus a is b over s, and the integral will be s plus a plus 1 plus 1. So, 2, and then we have s plus a plus 2 and a constant. Now, what we do here, y we can take. So, b over b x square over, so s plus a, here we have s plus a. So, the square term will left. So, b over s and s plus a plus 2, and then we have the c term and x power minus s plus a. Now, we take the Laplace transform of the boundary condition, and boundary condition was y 0 t is 0. So, here we get y 0 s is again 0, and then we see that x is equal to 0, this is 0, and in fact, we can just easily see from this equation, when x is equal to 0, this term is 0 and this is 0, c will be 0. So, this implies that c is equal to 0. So, our y x s, we have b x square over s and s plus a plus 2, and this we need again this partial fraction. So, we have b x square, and for these two terms we have 1 over s, and if we have here s plus a plus 2. So, let us see what we get, s plus a plus 2 minus s. So, we get a plus 2 extra there. So, we have a plus 2, we have to divide. So, these are the partial fraction, and now if we take the inverse Laplace transform, so we will get y x t will be b x square over a plus 2, and then the Laplace inverse of 1 over s, we have 1, and minus the Laplace inverse of this function, this is e power minus a plus 2 t. Okay, so now we move to the partial differential equations of second order, and we take the following heat equation. So, we have del u over del t is equal to del u over del x square, x positive t positive, and the conditions are given. X 0 is 1, that is the initial condition at time t is equal to 0, and the boundary conditions at x is equal to 0 is 0, and the limit as x approaches to infinity u x t was also given. So, these are the boundary conditions. And now, this model says as I discussed already, a phenomena of the heat conduction. So, if we consider this infinitely long metal bar, so in that case what we see here, that initial if we see this u, if we think this u as a temperature. So, the initial temperature was that is u x 0 was 1, and this end of this bar is kept at 0 temperature because it is given u 0 t is 0, and this end as x approaches to infinity, the temperature is again 1 as the initial temperature, because we put this end at 0. So, here the conduction will take place, and as x approaches to infinity, still the temperature is 1. So, now we are interested to find this temperature, that means the solution of this heat equation. So, we take the inverse Laplace, the Laplace transform. So, taking Laplace transform both the side, what we get. So, we have s, and the Laplace transform of u we denote by x s minus u x 0, and the right hand side d 2 over d x square, the Laplace of x s, and this is given. So, u x 0 is 1. So, what we have, this differential equation d 2 over or d2u over dx square and minus s and u xs, this is minus 1. This we can solve. This is the second order differential equation with constant coefficients. So, its solution will be u x s, the complementary function, and plus this particular integral, and the complementary function will be c1 because this characteristic equation will be m square minus s. So, the roots will be square root s plus minus. So, c1 e square root s x plus c2 e minus square root s x. So, the particular integral you will get t square minus s, and we have minus 1 here, we think as e power 0 x, and then we get this 1 over s, this 0 we can put it here. So, we will get minus s. So, we have 1 over s. So, this solution u x s is c1 e square root s x plus c2 e minus square root s x and plus 1 over s, that complementary function. So, now we consider the boundary condition, and the boundary condition was u 0 t is 0, and from here we will get that u 0 s is 0, and we have the second boundary condition that as x approaches to infinity u x t is 1, and this implies limit x approaches to infinity u x s, and this is the Laplace transform of 1, and this will be 1 over s. So, we have taken the Laplace transform both the side of both the differential equations, and now we use to get this constant. So, with the first condition what we have, which is u 0 s is equal to 0, will give us the 0 is equal to c1 plus c2 and plus 1 over s. So, this is one equation, and when we use the second one, that means the limit x approaches to infinity u x s is 1 over s, this will give us 1 over s, and the limit as x approaches to infinity, the first term is c1 e square root s x plus the second term was c2 e power minus square root s x. So, as x approaches to infinity, s is positive. So, we will get that term 0, and we have 1 over s. So, this 1 over s, this 1 over s, and then this limit. So, this is possible when the c1 is 0. So, c1 is 0, and then c1 is 0, we can get the c2. So, c2 is minus 1 over s. So, the solution is then that u x s minus 1 over s e minus square root s x plus 1 over s. This is the solution. Now, we take the Laplace inverse Laplace transform, and this will be u x t is, so 1 over s, it is 1, then we have minus and the Laplace inverse of 1 over s e minus square root s x. And now, this one, if you remember, so we recall that the Laplace of error function of k over square root t was 1 minus e minus 2 k square root s over s. So, the error function, you can see here the error function k over square root t will be the Laplace inverse of this, that is 1 minus and the Laplace inverse of e minus 2 k square root s over s, and this is exactly what we need here, Laplace inverse of 1 over s and minus square root s. So, this k we can substitute x by 2 to get exactly the result. So, what we have then 1 minus, and this we will get 1 minus the error function. So, 1 minus the error function k is x by 2 square root t. 1 will get cancelled with this one, and we have error function of x over 2 square root t, and this is the solution of that heat equation. Okay, so the next example, that is again an example of heat equation, 2 del 2u over del x square subject to the conditions u 0 t is 0 and u 5 t is 0. These are the boundary conditions given, and we have initial condition at t is equal to 0, that is sin pi x, initial condition. So, now we solve taking the Laplace transform both the side of the equation. So, here we have, let us first take for the right hand side. So, we have 2 del 2 over del x 2 and u x s, and then we have minus, for this we have s u x s, and then minus plus u x 0 and is equal to 0. So, this is sin pi x. So, we have d 2 u over dx square minus this s by 2 u x s, and this we take to the right hand side, we have sin pi x over 2. So, again in this case the complementary function would be a constant e power square root s by 2 x and plus another constant e power minus s by 2 x. The particular integral, we get 1 over this t square minus s by 2, and we have here minus sin pi x by 2. So, we have minus half and this sin pi x, and here we have minus pi square, this d square will be replaced by minus pi square and minus s by 2. So, this is sin pi x over s plus 2 pi square. So, now the solution is u x s as c1 e square root s by 2 x plus c2 e minus square root s by 2 x plus sin pi x over s plus 2 pi square. Now, the boundary conditions, and these boundary conditions are u 0 t is 0. So, this will give us u 0 s is 0, and we have u 5 t is 0, and this will give us the u 5 s is 0. So, the first boundary condition u 0 s is equal to 0 will give us here the 0 c1 plus c2, and this is when x 0, this is 0. So, the second condition 5 s is equal to 0, we will get the 0 is c1 e s by 2 into 5 and plus c2 minus s by 2 into 5 and plus when 5 pi sin 5 pi is 0. So, from these two equations what we see that the c1 and c2 both are 0, c1 is equal to c2 and they are 0. So, we have the u x s sin pi x over s plus 2 pi square, and now we take the inverse Laplace transform. So, we will get u x t sin pi x as it is, because the Laplace inverse was with respect to t, and we have 1 over s plus 2 pi square. So, this is nothing but e power minus 2 pi square t. So, this is the solution of this heat equation. Now, we consider the example of one dimensional wave equation, that is del 2 y over del t square is equal to a square del 2 y over del x square, where x is positive and t is positive. So, in this case we have subject to the conditions that y at t is equal to 0 is 0 and also y t. So, we have the double derivative with respect to t. So, we need two initial conditions. So, partial derivative of y with respect to t at x and 0 is also 0. So, these are for x positive, these are our initial conditions, and then the boundary conditions we have at 0 t. So, at x is equal to 0 we have the function sin omega t, and the limit x approaches to infinity y x t is 0. So, these are the boundary conditions. So, if we just look at the physical phenomena this equation models. So, we have a string here and this end, as we see this boundary condition. So, this is the displacement or the solution y x t. So, at this end of this string we are moving with this function y 0 t is equal to sin omega t, and y 0 t, and as x approaches to infinity. So, this limit as x approaches to infinity y x t is 0. So, this is fixed, this end is fixed, and then we have the initial conditions that y x 0 at t is equal to 0, it is the string is in rest. So, y x 0 is 0, and also the velocity y t x 0 is also 0. So, the string was in rest, and then this end we have moved according to the sin omega t as t varies here. So, now the solution of this wave equation, we again take the Laplace transform of that. So, we have s square y x s minus s y x 0 minus y t. So, the derivative with respect to t x 0, this is the derivative theorem for this, and then we have minus a square, the second derivative d 2 over d x square, and we have y x s is equal to 0. So, what we see then y x 0 is 0 and y t is also 0. So, these two terms vanish, and then we have s square y x s and this term. So, let us just rewrite again. So, we have d 2 y over d x square minus s square over a square and y is equal to 0. And now, its general solution, it is easy. We have only the complementary function. So, we have y x s is c 1 e s over a. So, the roots are s over a plus minus s over a. So, s over a x plus c 2 e minus s over a x. Again the boundary conditions. So, one boundary condition is as x approaches to infinity y x t is 0. So, from here we will get that the limit x approaches to infinity y x s is 0. As x approaches to infinity, this y is 0. So, from here we can see that our C 1 is 0. So, this implies that C 1 is 0, because here we have e power s over a x. So, this will grow unboundedly. So, we have to have the C 1 0 to guard this 0. So, then our solution is with the other constant minus s over a x, and then we can apply the second boundary condition, which was y 0 t as sin omega t, and if we take the Laplace transform here, we will get y 0 s omega over s square plus omega square, and then we apply to this equation. So, we will get omega over s square plus omega square is C 2 and this x is 0. So, we have just this C 2, this constant. So, we get y x s is omega over s square plus omega square e minus s over a x, and now we can apply the second shifting theorem to get this inverse. So, this is simply y x t, because this is sin omega t. So, we have sin omega, and due to this shift we have t minus x over a, and we have Heaviside function t minus x over a. So, this is the solution. Now, we come to the last example of this lecture, and that is again a wave equation problem. So, we have the equation u t t is c square u x x, x is between 0 1 and t is positive. The boundary conditions are u 0 t, u 1 t. So, at this and this end it is 0, and the initial conditions are u x 0 sin pi x, and we have u t x 0 is 0. So, we take Laplace transform. Taking Laplace transform of the equation, we will get s square u x s minus s u x 0 minus u t x 0 is equal to, we have c square and the Laplace of u x x d 2 over d x square and this u x s. So, this will give us u x 0 is sin pi x and u t x 0 is 0. So, here we get the 0 term, and so we have d 2 over d x square over this u x s minus this s square over c square u x s, and this minus s over c square, and we have this sin pi x, the initial condition. Now, again this general solution, the complementary function and the particular integrals. For the complementary function, we have c 1 e, the roots are plus minus square root s over c, s square over c square. So, this is just s over c x and plus c 2 e minus s over c x, and the particular integral in this case. So, the particular integral would be minus s over c square sin pi x, and we had here d square minus s square over c square. So, this will be minus pi square. So, we have s over c square and sin pi x over minus pi square minus s square over c square. So, the c square gets cancelled. So, we have the minus sign, also we have s sine pi x over s square plus pi square c square. This is our particular integral. So, our solution is u x s c 1 e s over c x plus c 2 e minus s over c x and plus this s sine pi x over s square pi square c square, and the boundary conditions are u 0 s and also at 1 both are 0, and this will, using these two boundary conditions, we will get the c 1 and c 2 both will be 0. So, our solution would be then u x s is s sine pi x over s square and pi square c square, and now we take the Laplace transform again. So, we have u x t, this is sin pi x independent of t or independent of s, and then we have s over s square plus pi square c square, this is cos pi c t. So, this is the solution of the given wave equation. So, at this point now we bind up this series of lectures on Laplace transform. So, we have introduced the concept of Laplace transform by solving various well chosen differential equations, different kind of boundary value problems, initial value problems, as well as integral equations, and the other applications of Laplace transform is beyond of the scope of this lecture. This was a rather introductory lecture. So, in the next lecture we will continue with the Fourier series and then Fourier transform. So, that is all for today. Thank you. Goodbye.